Okay, I'm audible. Yeah. Okay, so in the previous time I just proved the Rieslinder theorem, and now I'll tell about some implication of the Rieslinder theorem and some corollary of this. Okay. So first, it has So let's first consider another open set. So we construct that from if you as of now we just construct that we have an t equal to 0 surface, which is sigma, and we take a small time step which is just
that is coming out of the board, right? Suchetan.
Yeah.
So that time is orthogonal to the board, right?
Orthogonal
to the board.
Oh yeah.
Okay. It's fine. It's a
no.
It's okay.
So
because it may be confusing. So your time is y-axis and space is x.
Exactly.
Right?
Yes.
So if it is just two-dimensional, which means what sigma is a Cauchy slice, which is space-like. So it should be just one line.
Oh yeah. Yeah, sure. I mean. So this is the we construct this is just u u, okay, this is the u, and then we take another region which is just v. This part is v, which is a sub part of the sigma, and this whole part is we call that u of v. This open set. Now let us consider another open set, which is just v prime, okay, which is spacelike separated from v. So take v prime, which is now take any operator, any field operator phi, which is phi of x, where x belongs to u of v prime, okay, and take another operator a which belongs to u of v. Then from just from the microcausality, it is just obvious that a and phi x commute. Also for a prime, which is so it is true for, right? So when v and v prime are spatially separated, then it is true. This is my causality. Now we know. Let's assume some vector a, some operator a, which annihilates this vacuum state. Let's suppose that there exists some a in the which annihilates this vacuum. Now, hence there exists phi of xi, where xi belongs to prime, for which we can use that this is right, because
What is A?
A is some operator which belongs to uv. For I am saying that if A belongs to uv and x belongs to uv prime, if v and v prime are spatially separated, then it must commute. This is just statement of macrocausality.
Just the notation, like UV is the region, right? So you mean the algebra on that region, right?
Exactly.
Yeah. So A belongs to local algebra on UV. That's all. Yeah.
So since A omega is 0, so this is also 0. So again, since A and phi commute, so from this we know that A right. But now from the Rieslinder theorem, we see that if you take all the operator localized in this region, I mean UV region, this UV region, then this state cannot be 0. Phi x1 to phi, this state cannot be 0, right? So if this must hold, then it implies that A equal to 0, right?
It can also imply that A is not does not have support only in UV, right? It can have support.
So I can't hear you. Sorry.
Yeah. So it could also imply that A is not space like. I mean, there does not exist an A that is localized only in UV, right? Like.
Yeah. A is localized.
So I'm saying only. So I'm saying that it does not. It need not imply A is 0, right?
No, I'm saying that if this is true, right, and this state, this phi x1 to phi xn acting on omega, this as from the Rieslinder theorem, this state cannot be 0, right?
Correct.
It is a span of all states, right?
Correct.
So if this is non-zero, then imply that A must be 0.
I'm saying that to bring it to this form, you commuted A across the fields, right?
A across?
The fields. You commuted the A across all the fields.
Yeah.
But I'm saying that need not be also true, right?
No, but that is true from just from this.
No, that's what I'm trying to say. Why does this imply A equal to 0 and not imply that there does not exist an A that can be localized? I can have an A that is completely delocalized and still annihilate the vacuum, right? Isn't that a corollary?
No, but I am already assumed that A is some operator which is localized on this V prime, right?
That I understand. I'm saying that you're not saying that there cannot exist an A at all. You're saying only in some localized UV that they cannot exist. That's.
But what is the problem?
You can have an annihilation operator which we know exists, which exists all across space-time, not just in some localized fashion.
Right. I'm saying, so it can imply that, right? Not just that there does not exist an annihilation operator.
Yeah, I mean, that means that there is no operator A which analyzes any state. I mean, sorry.
There's no local annihilation operator.
Exactly. But what is your point?
I'm saying that. So you assume he's also saying the same. Okay, fine.
But
go ahead, maybe
okay.
If it comes again.
Okay. So this statement tells that that there is no local operator A in this state which actually annihilates this any state in this. So okay, now let me define two things.
Is the statement that omega is separated?
So now define two things, which is cyclical separating. So we'll tell that A vector Okay. So we just define a vector to be called cyclic. A state is called cyclic if with respect to an algebra, I mean algebra observables AU, which I will define later. What is algebra observables? So only if the state that the state psi, and if we take if any vector A, which is like which belongs to this algebra observables in that localized region, are dense in the Hilbert space. So this basically state that from the Rieslinder theorem, which tells that from RS, this implies that omega is a cyclic state, right? Because as I said that acting on any operator on omega, any localized bounded operators on omega, you can take any other arbitrary state in the Hilbert space. That is means that it is dense in the Hilbert space. So okay. So it's just a definition that it is called cyclic state, and another is separating. So separating state means that basically that if psi is and vector is called separating with respect to that algebra, if any operator acting on psi is 0, it only implies that this operator itself is 0, because there exists no operator that annihilates this state. So this is called separating state. So again, from the Rieslinder theorem, we see that vacuum is a separating state. And also the point is that that if omega is cyclic in, okay, so the from this side and just from this example, we see that from this see that if psi is
Suchetan?
Yeah.
So just to understand, so if I choose U to be the full space-time, then is the vacuum still separating?
Then?
Is the vacuum still separating?
Then
if
the vacuum state is cyclic.
Separating.
U to be the full state.
If AU, so the U is my open set, right? If U is for me the entire space-time.
Okay.
Okay. Yeah. Then is the vacuum, because it depends on what the AU is, right? For which this is. So if my AU is the full space-time, is the vacuum still separating?
Is the vacuum state? Yeah, then I think because there is annihilation operator, right? I mean, which operator acting, but this annihilation operator is actually that it has support in the full space-time.
Full space-time. Right. So then it's not separating.
Of course, it is. I mean, it is not separating.
It's not separating.
But it is only in the level of algebra. I mean, of some localized region. So all these things, some local QFT.
Okay.
It is always related to some local region or something.
Okay. Okay.
Okay. So I'll tell what is the algebra meaning. So it is a local algebra. So it is always defined on the some local region.
Okay.
Not on the full spectrum. Yeah. So from these things we see that if psi is separating in AU, then that implies and so as we see that that we assume that this is cyclic, right? This sorry. This is cyclic. So from this example, this is cyclic, but xi is around the UV. So in this example, we all assume that this omega is cyclic in V region. So this implies that omega is separating in A. Separating in U prime, because A belongs to U prime, right? Sorry, here it is P prime. sorry. So if an operator is cyclic in the algebra observable of one subregion, then it is separating in the algebra observable of the complement region, okay, or the other region, and the vice versa. You can do so cyclic means always separating for the complement region. And since omega is actually separating in since omega is also separating in both v and v prime, so it is cyclic in both v and v prime, or all the others.
Can you say again how is it dense there?
Oh, dense? No, dense means just that as I said in the Rieslinder theorem, that any state can be is approximately closed by acting operator which is localized in this region, this uv prime, uv, right? So you take any operator phi, and acting on this omega, you get whatever these states is a full Hilbert space, the states of full Hilbert space, the states of full H naught. So all the states in the H naught can be well approximated by acting on local operator in the UV, acting on this vacuum state.
This last statement, if psi is separating in AU, how are you getting that there? Yeah,
so that if psi is separating, that means so you see the vice versa is true, right? That if it is cyclic, then it cannot be separating. It must be separating. So if you consider that if it is separating, like there exists no A acting on omega equal to 0, then there is no reason to this to be 0, right? So this is dense. This is not 0. This is just a reverse statement of this.
But
I just show here that if it is cyclic in one algebra, then it is separating in the
other
complementary algebra. So since it is, this Rieslinder theorem is both true for V and V prime, right?
Right.
That it is cyclic. If it is cyclic in V, we can also prove that it is cyclic in V prime. You can take any region, right? If V prime is the region that you can so Rieslinder theorem is true for this V prime region.
So what if it is separating in both regions? But
separating means that there exists no any vector which annotates this state, any state of this, for which A psi, that is separating, that there exists no operator A which acting on psi is 0, except that A is itself 0.
But how does that imply it's cyclic?
How does that?
How does that imply it's cyclic in the other complement region?
How does that mean cycling the others?
You just showed that phi is acting on omega is not 0.
Yes.
Okay,
how
does that mean it's
how to
dense?
reverse it?
Okay.
Okay, so let's
the statement, if psi is separating in AU, it implies psi is cyclic in AU prime.
No, he is saying that how to prove reverse. Here I just take that if A omega is 0, then I show that it cannot be 0 unless A itself is 0. So he is saying that if we don't,
the state
how to
is
go
cyclic,
other way around.
He went to showing that it is separating in the complement. But he's saying the reverse is also true. But there, if you assume it is separating, you just get the statement that phi, all those phi's acting on omega is non-zero. From that, how do you show it is a dense?
I have said that if psi is cyclic, then it is separating in the other side.
Yes.
Now you are saying that other way around. No, I think I don't need that, because from the Rieslinder theorem we said that if we take any region V or even any region V prime, then the vector psi is always cyclic with respect to V and respect to V prime. Like omega is, so omega is already cyclic in that sense.
But we are talking about some other state psi, right? Not
no, not for other state. But
you're talking about
for
general
other
state.
You have, if you want to prove, then you have to consider. I mean, so for other proof, but from recent it is true for at least omega. I mean, for vacuum state. For vacuum state, it is already cyclic. Then I saw that it is also separating with respect to other. It is only what I am already considering. It is for vacuum state. Okay. So yeah. So vacuum is cyclic and separating for this system, and one implies the other. So because vacuum is already, I have proved that vacuum is already cyclic in. So and now it is also separating. But for other state, which is, then you have to first prove that which is cyclic. What do you mean by? I mean that state is cyclic for some observable. It is not proved. I have not proved that. I have only proved that omega is cyclic. I mean the vacuum is cyclic. But for it was I can so that a class of set if you consider like which you constructed out of only okay, well I'll tell that later, but out of like invertible operators, okay, like and if you construct the state, I mean operator like state like this, like where where A and A inverse exist, then this state is also cyclic and separating. It can be proved, and I have planned to show the modular for excited state, where in some paper by Laskari, Liu and something that they consider this type of state, that they show that these are actually cyclic and separating, where there exists A and A inverse. I mean it is invertible, A and inverse. So this class of states is also cyclic and separating, but not all class of states are cyclic and separating. Okay.
Sucheta, just I have a doubt. This A belongs to UV prime.
This?
Yeah. And omega belongs to UV.
Omega?
Yeah, the state omega.
No, omega belongs to any. Omega is not a localized state. Omega state means it is described anywhere, right? It is a I mean state in the full Hilbert space. Omega is not an operator. A is an operator. A belongs to some region. State does not belong to any region. Right?
Okay.
Omega is a vector. It does not have any. It is defined in all over the place. A is the operator which belongs to UV, and X, and phi is the operator where xi belongs to UV prime. Okay. So these two actually tells that. So this cylinder plus this separating thing actually tells that. So so we have only assumed that in the to prove the cylinder theorem, we assume the what is it? Pointer invariance of vacuum plus, and here we assume the microcausality. So from these two basic principles we have seen that this omega is cyclic and separating. So we have not assumed any other constraint or any other rule. So we just assume Poincare invariance to prove Rieslinder theorem, and we just use microcausality to show that it is separating. So from this we see that this vacuum is cyclic and separating.
Shift the.
Oh, sorry.
Suchetan. Hi. Here.
Yeah.
When did we use the full Poincare? We just wanted some Hamiltonian, right? Like in the proof you showed us. Did you really use the full Poincare? I thought we just used the existence of some Hamiltonian or something.
Existence of Hamiltonian.
Right. We just time translated and said Hamiltonians are bounded.
I mean, yeah, that is the Poincare invariance of my. Okay. I mean, you are saying that.
Did we really need full Poincare?
Exactly. That h greater than 0.
Yeah, but did we really use full Poincare? Like, did we need Poincare? I'm just wondering.
Actually, I need Poincare to show. Yeah, it's a good question. Yeah. So I have just shown that this phi xn have shifted xn to xn plus ut, right? But if I show it, it was any direction, not just time-like direction. Like it is like xn plus some uxi, but some uxi or something, right? Then you have to, then you have to use that Poincare image like p mu acting on omega is 0. Because I only showed that this is just we just take that time-like direction. We just shift it time-like direction. So we can expand it into either IHT, phi xy, the minus IHT.
You end up using translations as well. Translations are not bounded, and then part of that proof, like
translations are not bounded, but H is the time translation increase, right? So it is bounded operator. H is the time translation operator, but p mu acting on omega is 0, right? If I just if you assume the Poincare invariance.
no, but you agree we didn't use translations in what you showed us.
No,
right?
I have not used, but if I take this shift of this xn to be
Yes,
any-
and
any
then you have to talk about analyticity and so on in space-like directions.
Exactly.
Since P is not bounded,
Exactly.
that same argument you showed us wouldn't work.
No. Yeah.
So
But
I'm
it
confused
can
what
be
you're
proved,
saying.
but it is difficult. So, but it can be proved, but it is difficult.
Okay.
It is.
I thought it was related to the fact that if you given that you have a Hamiltonian and you just have one time-like translation,
Exactly.
okay, you will not be able to span the full space. You can only go in some direction. For it to be able to span, you have to choose a different time-like vector. That would be space-like translated with the initial time-like vector. You get what I'm trying to say? Like if you take this field and then move only in one t, you're actually you start with some u.
Say you want to go the full cone.
You want to do the full one, and you want to go back. You want to flip
Exactly.
the entire main cause.
So it is only just one direction. I just showed that only one direction, only time-like direction, not in the specific direction or something. So for this you need the full Poincare invariance.
Would you say that one particle states are not cyclic and separating? Would one particle states be cyclic and separating?
One particular state. Why?
I'm asking. In idea, I would expect it to not be.
Yeah, but for one particular state, but for that H, it is not 0, right? H psi is not 0. Then to prove this cyclic, you have to. It is difficult to prove. Here we already assume that H acting on psi is 0.
No, but could one say that it's like for example, if you wanted to get the vacuum state from a one particle state, you would have to act with the annihilation operator, which is completely non-local.
Would have completely non-local. Yeah.
And therefore, that should imply that the one particle state is not cyclic and separating. One particle state, but it won't be cyclic, no?
But that is you.
It won't be dense. Exactly. It won't be dense.
No, but Chandramal, your argument would say that the one particle state would be separating, right? Because if you take the algebra, which is not the full space time, then there is no operator that can actually act on the one particle state and
Yeah.
0, right?
But that is also true for vacuum, right? You have some annihilation operator, and if you consider the full space time, then you have some annihilation operator, and it acting on omega is 0. That's not separating. But that is if you consider the full space time. But here I am just local algebra. I consider some localized region and local QFT. That's true for only for local QFT.
Suchetan, in the definition of separating, is it every A belongs to AU or like some A belongs to AU? What in the definition of separating, like you mentioned, did every A in AU had to annihilate psi, or was it just some A?
No, for any. Now, if there exists some A psi acting on 0, if there exists
Some A,
operator A psi,
some A.
then
Okay.
it must be 0. No other operators. Sorry, language.
Suchetan, one question. So, in a given sector, let's say the vacuum sector, is the cyclic and separating state unique? Like the
Vacuum.
is the only state which will be
No.
It's not.
No. Vacuum sector by define is the
Yeah. So it's built on this.
this. Yeah.
Yeah,
But there would be other cyclic and separating sector as
yeah,
M vector.
so
That is not for the
another
vacuum
super
sector.
selection sector. But in this one, this is the only
Only one. Yeah, I think so. Yes,
Yeah,
sir.
so that means the single particle states, where do they belong?
One particle state.
Yeah, one particle state.
No, but
Which means,
one particle state, where do they belong?
yeah, I mean, if you act with just one single creation operator on the vacuum, you will get one single particle state.
But this thing, I mean, that creation operator is not local operator, right? That is A operator. I mean, there is global. I mean, that is integrated over full space-time region.
No, if you have the fields,
Huh?
if you expand the field, and then at each point you will have A and A diagonals, right?
Yeah, but this A is basically what is D4P. I mean, these are integrated operator. Even in the full, it is integrated over full space-time region, right? If you write the expression of A.
If I write it in momentum space.
Yes, it is integrated over all momentum. I mean, if you I mean Fourier transform in the spatial, it is not a local operator. A
A
is not a local operator. A is not a local.
Field is local.
Huh?
Then let's say if you write some field phi of x equal to integral. I mean, if you integrate it over the momenta, so then you will have A diagonals and A with some coefficients. Right? So, isn't this defined at a particular point in X, the creation and annihilation operator?
No.
Like for
But
Not in the usual sense, right? I mean, it's like
But-
saying that if your field is local, then the momentum conjugate of that is not local.
in momentum it is not,
Correct.
but in the configuration space,
But then
like here we are talking about everything in space time, right? So all these points were in space time.
what is your definition of creation operator? Is it the same thing as AP, or is it like AP dagger, or is it something different?
See, if you write AP dagger as, if you just write it as 5 star e to the ikx, now the e to the ikx is your smearing function, right? And you integrate over here.
No, we integrate over K.
But I think what he's saying that if you do an inverse Fourier transform and try to write AP dagger in terms of phi and phi, then you find that if you do an integral over all positions.
yeah. If you inverse Fourier transform, it means that.
But now the smearing function is never local. That smearing function, because
Yeah,
it's
it's
placed
extended to that,
it's everywhere. So you cannot localize that, right?
Yes. Yes, you're right.
So now I'll come to the that.
Suchetan,
Yeah.
can you say what is the meaning of separating apart from this mathematics?
What is the meaning of?
Separating state. What is the meaning of separating?
Yeah, this means that there exists no. I mean, there is if omega is separating, then there exists no operator A which can annihilate this. No operator A where A belongs to the algebra operation of U. So in that algebra observable, from where you are defining this vector is cyclic or separating, then there exists no A in that region which actually annihilates this state omega. Except this A is itself 0. I mean,
Okay.
so there exists no operator A which annihilates this.
No, the point separating, does it separate anything?
Separate?
Anything? From
Oh, I don't know.
yeah.
Sorry, I
Okay.
don't know. Then
Okay.
I don't know why the source of the name. I don't know even why it is cyclic. I don't know. I don't have any. So it is what you were saying last time, that there is So it seems to be a bizarre bizarre theorem in the sense that so that means that by acting on so suppose you take an operator and you act that operator acting on the vacuum which is supported only in a very small region, UV, and you can create whatever you want in very long distance and very arbitrary. I mean, suppose this okay. So suppose this is the region which is U, and this is the region which is suppose U star. Okay. So you are here and you have some laboratory, and you so you want to apply Rieslinder theorem practically. So you suppose you have some measurement operator, etc., and you want to create suppose a moon. So it was suppose you want to create a moon in very long distance, in very long distance where I mean this is the okay. So how should I say? Okay, so suppose we have an operator M which is called the moon operator, okay, and you want to create this. So from this operator you can create a moon in very distance which is V star. Okay, this is very distant region, and so where U and U star actually space-like separated, very distant region. So now here is the observer, and so we have the state omega for which does not contain this moon operator, so which is approximately 0, right? In vacuum it is not approximately 0, but it is but for which state it actually contains this operator. Then for psi is the state which contains the moon operator, then it is actually 1. So if we have the operator and we acting and we measure the operator in the psi state, then we get actually a moon, right? In the very distant space.
Can you elaborate what are you doing right now? So you're trying to, this is.
Sorry, I can't.
Yes.
Hello. Yeah. So you are trying to apply some operator on this omega state, and that operator is in the algebra of U. Is that correct?
Operator?
So what are you doing right now? Can you explain?
No, I am saying that I have an operator M. Okay.
Which algebra does it belong to?
Yeah, it belongs to M belongs to this A of U star.
Okay, U star.
U star.
Fine. Now, what is this moon story in maths?
What is?
In mathematical expressions, what is this moon story that you're talking about?
What is this moon? This is.
Yeah, you're going to do something. So
yeah, I'm saying that there is a state which is a vacuum state which does not contain this moon.
What do you mean it doesn't? So where
the expression value of this moon operator in the vacuum state is 0, approximately 0, and the expression value of this operator in some state is not 0. Like you can take any of suppose suppose like in CFT lab, suppose suppose 1 point operator in vacuum is 0, right? But it is on some state like psi it is non-zero. So in some state it is 0, but in some state, so it belongs to that state where it is non-zero. I am saying that in this state it is 1, approximately 1. So which belongs to, you can, this means that you have some operator, but you must measure this in the state where the expression value of this operator is 1, non-zero.
Where is the moon going to pop up? U star or U?
M belongs to U star.
Okay, so
yeah, the point is that the point is that using from the Rieslinder theorem, we know that we can create any state psi by acting some operator in U. Let's A belongs to U operator. Okay.
That's okay.
So acting in any state U, you can get state psi, right?
Yeah.
Yeah.
Okay.
So that is you want to. So after okay. So from the Rieslinder theorem, you want to apply this Rieslinder theorem by taking some operator in this laboratory, and he act this on the vacuum, and then he can create some state psi, and then he measure the operator M, which can create a moon in very distant place U star. Right?
Okay. Okay.
That is the point.
Okay.
Now, okay. So from this we can see that okay. So from this
I have one question here. So you are using approximately equal to.
Would it matter?
Yeah, approximately means it is okay. Approximately, you can take it as 0. For instance, it is 0. Approximately means because it might not be, but because we don't know what is M operator or something. But let's say it is 0. Okay, it's not approximately, but it's not. It does not matter. It is approximately or not. But and it is approximately 1 means that it might be some other number also. But okay, I'm telling that it is 1. It is some normalized and it is 1. But okay, but it doesn't matter.
M is not the same thing as A. M and A are not the same.
A and
M are not the same in this example.
A and M is not the same. No. M belongs to, okay, so let me, M belongs to AU star and A belongs to AU.
Is M like the projection operator for the moon?
Yes, you can say that. But yeah, but okay. Right, we just take psi as A omega, so you can write this. Now the point is that since we said that M belongs to AU star and A belongs to AU, then this commute, right? A and M commute.
Just a question. This A is that annihilating operator?
A. No,
annihilation operator is not is any operator.
Any operator.
So
any
you are
operator
acting this A and on omega, and you are getting some
state
psi.
some approximately some state psi. Approximately close to psi.
That is not annihilation operator.
I mean, excuse me. I mean, like maybe I mean I got messed up with the notation. This A acting on that vacuum. I mean, previously you had defined some A which belongs to A mu or AU, okay, and it was an annihilation operator, right?
No,
so
it's not anything.
I mean, maybe I missed something.
No, there is nothing annihilation or creation operator. I am just saying that from the Reed-Cylinder theorem, we see that we can take any operator belonging to some algebra. Then we can, and if this state is cyclic, or since omega is cyclic and separating, cyclic state, then we can get any other state in the Hilbert space by acting some local operator on this state omega, right? That I want to use, and he want to use this.
Okay. So if omega is not cyclic, then
no. If omega is not cyclic, then he can't do this.
Okay. Okay.
And then on that vacuum, what you are saying is that what Dirichlet is also saying, because it's cyclic, is that I can create any state in my Hilbert space with just operators localized in some set U.
Okay.
He's just considering some random operator A, which creates a state in which if I have a moon operator, it will be an eigenstate of this.
Okay, fine.
Exactly. So we know that A and M commutes because it are two specially separated region U and star. Then this means that we can write as up to this is nothing. I mean it is all fine. But now if we use that A dagger A is 1, if A is unitary, then A dagger is 1. Then this means equal to 1, right? But here we assume that omega is 0. So these two are, I mean, so this seems to be paradoxical, right? Because so this means that we only assume that A dagger A equal to 1. So this is not true. So A dagger A is not 1. I mean, and so this means that Reed-Cylinder is also consistent with the Reed-Cylinder theory, because Reed-Cylinder theory does not tell about anything that we have to take unitary operator. So I mean, all that it said that you need to act some bounded operator in this algebra, from this algebra, and you should act on this omega. But this should not be any unitary operator. So and we see that for unitary operator it is not true. So this means that using any unitary operation or some real operation, you cannot create a moon in this place. So you cannot do it unitarily. Okay. but it is not a conflict between recylinder theory and some unitarity or something. Okay. And also another thing is that this right. So this not equal to this into this. So this means that it has a correlation, right? Because this means that M and A dagger A is correlated. But this has non-zero correlation, right? Because I mean any what I'm saying, like suppose if you want to consider the correlation of A and B, so just some state omega AB minus. So this is the measure of correlation, right? The connected correlation piece. So if this is 0, then it is not correlated. But it is non-zero. If it is 0, then it is not correlated. But it is non-zero, then it is correlated. So this example suggests that this M and A dagger A is actually correlated. But though these are two different part of this system, M belongs to AU star and A belongs to this AU, but still they are correlated. There is some sense of entanglement, right? So that was my first point, that field observables in some region is actually entangled with the field observables in another region. That is an evidence of this. Okay. So this is the end of the Rieslinder theorem now.
Suchetan, can you repeat the argument? You are saying that this thing is not equal to that.
This is
that omega M A dagger A, omega is not equal to omega M omega. So how this is implying M and
A dagger A is correlated.
Can you repeat it again? Yeah, can you repeat it?
Can you?
Repeat it. I mean, I could not follow.
That is not correlated.
No. Can you repeat?
He's basically saying that if they were correlated, then equality should hold.
Yeah, but it cannot be okay. Oh, sorry. If it is, because you see that this is actually 1, right?
Yeah.
And but this is actually if this correlates, then it is 0. It is 0. So 1 cannot be 0, right?
Yeah.
So it cannot be this.
Yeah, this is fine.
Okay.
From here you are saying they are
Now from this I say that if any two operator, this is a measure of correlation, right? That this minus this thing. I mean AB minus A into B.
Yeah.
This is a measure of correlation, and it is non-zero here. So there is a correlation between M and A dagger, though they are infinitely separate. I mean they are very far away separated, spacely separated, but there is still some correlation between M and A dagger. So I am saying that from this you can see that that notion that in field theory in a vacuum, that any operator in the region, some region is entangled with some field observable in the other region. This is some sort of, which I was saying first that recent theory is telling that it is an entanglement it is the entanglement at the level of operators, at the algebras of operators, not just the state. That is very Now I'm going to define local algebra. So from Rieslinder theory, we see that the algebra observable in local region is very useful thing, and it has some property of entanglement. Now I'll define what is local algebra. And for this you need Hugg's book of algebra. So these very abstract things. Let me just. Oh, the book. Sorry, I forgot the name of the book, but. Huh? Oh, sure. Yeah. So let me, this is very abstract definition, and I'll just write down. It has no very conceptual meaning. First, let us define that set of all bounded operators which is acting on the Hilbert space H is denoted by B of H. Okay, just and notation. One is that now we'll take a sub algebra. Let us define a sub algebra. So what is mean by algebra? So algebra means that for any A, B belongs to A, so the meaning of algebra that if A, B, two elements of the algebra A, so it defines an algebra if the linear combination of alpha A plus beta B, it also belongs to this algebra, and AB belongs to this algebra. And alpha beta is any complex number. Okay. Now I'll call what is star algebra. So it is that there exists an antilinear map So star means that it is a map from algebra to algebra. It is an automorphism, but which so this star operation means that if we take A star and we take double star, it gives again A, and the star of the AB is basically B star and A star. So this is the property of a star operation. So we define an operation, antilinear operation, which is called star operation, which is this. Okay. And if there exists this star operation in the algebra, then we call this as star algebra. This is just formal definition. Now we can also define a map is called a norm. If it satisfies the following property, one is like
Why is it anti-limit?
Oh, why?
If you have alpha A, alpha B, let's say an
It is-
imaginary number, the star would make it. It's not linear, right? If there's a minus sign, that will come. So that's why it's
Alpha star and all? Complex part.
Linear is omega A plus omega. That is also property of infinity. So we called a map. Map is called a norm. We denote it by this double line, which actually map from operator algebra of the algebra to some real number, or real number which is greater than or equal to 0. So we call this a norm. So it has the following property that if the norm of this any element A is 0, which means that A itself is 0, and it would also satisfy this property. These are just an abstract property, and so we'll call them if some operation satisfies this property, then we'll call this as a norm. Okay. For all and another definition is called C-star algebra. I'm just saying this because it might be important to okay, let me so C-star algebra is basically an if A is called C-star if so if it satisfies this following property that there exists a star operation and there exists a norm operation, and it satisfies that A star A, the norm of the A star A is basically the norm of A whole square, then we will call this algebra C-star algebra. But okay, this okay. So one example of C-star algebra is basically the for any Hilbert space H. I mean any Hilbert space H, the BH which I defined here, that BH is actually a C-star algebra. Okay, I mean all the bounded operators in the Hilbert space actually form a C-star algebra. This is an example. So like in quantum, I mean, and in that case, I mean in the quantum mechanics case, then the star is basically the dagger operation, right? And norm is the norm, size norm. So that is an, but it is purely in mathematical sense that here is no QFT or something in it. Now come von Neumann algebra. That is the main interesting part. I mean, all the following, I mean, discussion will be for the von Neumann algebra case. I think what Debangshu will also follow the von Neumann algebra discussion. So it has all the property of star operation plus it has an extra property which is I'll define the weak closure. So suppose that let so let's two state vectors psi and phi which belongs to Hilbert space. Then we can consider a sequence of operator let's consider a sequence of operators A1 to N belongs to BH. If it converges to A belongs to G of H weakly, then so weak closure means that that if we consider a sequence of operators A1 to An in the bounded Hilbert space of bounded operators, and if it converges to a operator A, which also belongs to this bounded operators of H, and if it converges weakly, this weakly means that the expression value of any two states psi and phi of An sorry, it's not expression value. I mean, if we consider these objects psi, n, phi, and take n goes to infinity, then it actually gives the psi a phi. So it is weakly convergent. It is true if like n goes to infinity, n, it is a, but it is not true. But if it weakly converges, that means that under any two states psi and phi, it is actually converges to psi a phi. Okay, it is called weak closure. So, and it is true for any state, right? Any two states. You can take any two states and any two states psi and phi. I mean, you can take any two states. Sorry?
I'm saying that for if any phi and psi, this statement is true. The condition that you have written, that An sort of as n goes to infinity approaches the expectation value for A, then doesn't that mean that as n goes to infinity, An basically approaches A?
Yeah, but it is that's true. But it is true for only this quantity, right? I mean,
but for any, if you consider any state in the Hilbert space, then you have basically classified the whole An, the full operator, right?
But that, why does it?
This series, this A, A1A, can contain unbounded operators. This is something.
Oh, when you're considering this sequence of operators, all of them are bounded, right?
Yeah.
Yes.
All of them have to be bounded.
And so is A.
Yes.
But then this statement should make sense.
This limit will not make sense. For example, if suppose limit n goes to infinity of An acting on something is 0, but limit of An dagger acting on something is not 0. This will not make sense. Then you cannot simply state it as an operator statement. You have to put it within expectation values.
Okay.
So these kind of things
What
can
is an operator statement to begin with? Any relation which is true between arbitrary state of the Hilbert space, right?
Right.
Just remove the thing. And
Yeah. So it's I would say it's a very formal way of writing. I mean, if you want to check whether two things are equal or not, you have to sandwich between states.
And if it holds,
you formally write that limit of this operator is equal to that.
Yeah.
That's it. But that last statement is a formal statement. If you want to check something, you of course have to sandwich.
Yeah, but I thought that statement, that limit n goes to infinity, An is A,
No,
is exactly this statement.
I got your point. If you tell that if it is true for on state, then then it is true that n goes to A. But exactly. I'm saying that it is weakly closed. If you just check that for any two state and it is go to psi and phi, then it is just we call it weakly closed. Just.
Yeah, if you can find states.
If you consider all state in the VAC, and you see that this is true, then it is itself what you are saying, that limit n goes to infinity, An is equal to A. That is true. But for that you have to check for all state, right?
All states, exactly.
Yeah.
So now here you are saying that if you can find any out of all the states, if you can find any two states psi and phi, and this holds,
then it is
you are
weakly
saying
closed.
This is weakly convergent.
Weakly closed. Yeah. That is the definition. There is weakly closed.
Yeah.
Exactly.
This
That is true. But if that is true, that if you consider all state, it is true for all state, then it is naturally that n goes to A.
Are there any stronger closure properties?
Are there any stronger closure?
Stronger closure property is something like if an acting on chi equal to a acting on chi. This is stronger closure, but this is not. I mean, we just want this property. Okay.
Can you not allow A to be outside BH, the limit point? So you're calling it closure, but A is already in the set.
Yes.
So can you not allow A to be outside B of H? Then it can be unbounded as well.
No.
So
A must be inside this B of H. No, okay. So
what is the point of calling it closure then?
What is that?
Closure. What are you closing?
Yeah, I mean, yeah, exactly. Like, so suppose, okay. Suppose, yeah. Suppose you just consider the set of all rational number, right? Suppose 1, 2, 2.1, 2.112, and you want to include root 2, etc. So you can I mean, what is the value of root 2? I'm sorry, one. Wait, sorry. Let's consider pi. 3.14 something 15 something it is. So you want to include in the sequence of operators like sequence of number like or rational number like 3.1, 3.14, 3.14 something. But you can include it. It is not included in that what you are saying, that it is not actually included in this, but you can include in the limiting sense, right? Yeah. That is what. Yeah.
Then Suchetan, here, like in the other slide, right? This AB norm less than A norm B norm. The last point.
Yeah.
No, here, like, yeah. Yeah, AB ka norm less than A norm times B norm. Like when is that satisfied? I'm not able to understand what does this really say. Or when is the inequality saturated?
No, I mean, yeah. So it is to some. It's like Cauchy-Schwarz inequality with something like.
Okay.
That is like if you take any. What is called Cauchy-Schwarz? Like yeah. So if you take 2 phi and the norm of phi and psi is basically that phi and psi. It is something, right? I mean, less than equal to. So Cauchy-Schwarz inequality also it defines a norm, right? I mean, it is true for a norm thing, and that is also this some sort. I mean, in ordinary quantum mechanics thing, this is the statement of Cauchy-Schwarz inequality. I think so.
I thought the first one is Cauchy-Schwarz. The inequality before this one is the usual Cauchy-Schwarz, right?
Oh, sorry. No, this one also, right?
The first one is triangle inequality.
Plus or product of 2, right?
Oh, the second one is Cauchy-Schwarz?
I don't know that.
Yeah, second one is Cauchy-Schwarz. Right?
Okay. It's
This
a
one
usual
is
thing.
Cauchy-Schwarz.
Okay.
I mean the product of this. Yeah.
Okay, thanks. Sorry.
Yes, yeah. First one is not Cauchy-Schwarz. Second one is Cauchy-Schwarz. So and so now I'm defining this because so von Neumann algebra is basically
Hello, can I ask this again? Like, I mean, is it really Cauchy-Schwarz? I mean, it seems to say variance is always less than mean ka square or something. Like, what? It doesn't make sense, no? Norm p square less than.
No, is that cos theta, right? Like AB cos theta. Like if you take the normal dot product, it's AB, the norm of A dot.
hey,
Can I just confirm expectation of x square less than expectation of x whole square. Is that what the inequality says? Seems to be wrong to me. Like no, expectation of x square less than expectation of x whole square is wrong. No, expectation. I think expectation of x can be 0. Expectation of x square is always positive, right? So it seems to be wrong to me. So, but or did we flip the inequality sign or something? What are you guys? I'm just saying it put expectation of x square a and b equal to x in some harmonic oscillator.
But is expectation a norm?
Oh, okay. But
I'm saying the norm, like the norm, usual norm is like.
okay, at least it doesn't look like any normal inequality.
No, this is a normal dot product inequality.
Okay.
Like if you have a dot b, right?
Oh,
A
okay.
is always less than equal to.
Okay. Sorry. Cos theta I understood now. Okay, thanks.
No, but it is true. I mean, it is Cauchy-Schwarz, right? I mean, in the user. Yeah. So von Neumann algebra is actually a weakly closed star algebra. Why define what is star algebra? And plus it has a weakly closure property, right? This property must have plus an identity operator. It must have an identity operator. Then we will call this algebra as a von Neumann algebra. Now some comments. Now I will define one thing: commutant. If
Suchetan, just a quick thing about the definition. So this is a normed inner product, right? Not just a norm. Norm is defined only for A or something, right?
Yeah, you can. I mean, inner product not, but yeah.
So,
but if AB is okay, okay.
Is
yeah, it's an inner product.
It's a normed inner.
Yeah.
Because you have A and B, right?
Yeah, for two operators, exactly.
No, you can multiply operators. A, B is still in your algebra, and you can take the norm. So right now, nowhere he has taken the definition of norm, but he's implicitly assuming it probably.
Yeah, but let's ignore that because we don't need that much of rigor. I mean, you have some norm. There's some notion of norm. At least in quantum mechanics, we know how to define a norm, and we can do that. I mean, even in QFT. So commutant, okay. So commutant is defined by A prime, which is defined as So commutant is an algebra which is defined by A prime, which actually consists of all the elements A which belongs to this BH, which actually commutes with all the operators B, where B belongs to any operator in A. Okay, so it is basically the set of all commuting elements of A is defined in the commutant algebra. Okay, so even the definition of A prime is basically this. So we can also define it by commutant.
Suchetan, sorry, I just missed it. So is von Neumann algebra is just a weakly closed star algebra or C-star algebra?
I think star algebra.
Just a star algebra.
I don't think C-star.
Okay.
Star algebra. But C-star is natural because of all the bounded operators in the Hilbert space C-star algebra. Okay. So C-star is even if it is C-star, then it is also von Neumann. I mean, it is not a problem. But just okay. Minimal requirement is weakly closed and star algebra.
Okay.
This is a minimal requirement. You just need to. So now I'll define what is okay. So A prime is a commutant algebra of A, and bicommutant is basically the A prime, which is defined as A double prime. So A double prime is a bicommutant. I mean the commutant of A prime. Okay, similar thing. And of course, yeah, you can okay. So this is because that, so A prime is actually the maximal set of commuting observables which commutes with A, right? And so that A double prime is the maximal set of commuting observables with A prime, which commutes with A prime, right? So A must be the subset of this A double.
So what is the bit? I mean, it's a subset. What's left out? Why? What's left out? A is a subset of A double prime. So that means some elements are left out. A double prime is bigger.
Yes, A double prime.
So what are the elements which are left out? Which are not in A, that are present in A double prime?
Oh, that is. I mean, you have to that is case by case. I mean, you have to define some algebra, and you can, like, okay. So one example, like suppose this is a region. Suppose it is a okay. Suppose this is a region A. Okay. So A prime is the all the observables that commute with A, right? So in spacetime region, it is a spacetime region A. Then this whole thing is A prime, right? Right? Because all the observables in A prime commutes with A. Now what is A double prime? So this is A double prime.
Okay, just a second. So when you said A, the domain of dependence of A would have been this only, no? For A itself, this would have been the set of operators.
Yeah, but A double prime is bigger than A, right? There might be some operators which does not belong to A. I mean, it is not.
When you said A, I thought you were talking about this diamond.
No. A means just this region, and the operator living in this region, in this slice. Not I'm saying not the operator living on the full.
Then why is A prime with the diamonds? A prime should also be only on the lines.
No,
you drew the domain of
set
dependence
of
of A
commuting
prime.
observables.
Sorry?
Which maximal set of commuting observables with A.
Oh, wait a second, yeah.
So all these observables which is living outside this causal type, outside this A, is also commute with this, right? But A double prime is a full region, full causal development.
Right. Those regions you have drawn are space-like separated to A. Okay, correct.
Right. But we'll see that for von Neumann algebra, actually A equal to A double prime. Because it is also, I mean, from physical point of view, because you just take some e to the power I-ish, I mean, just unitary evolve this operator into this whole setup, right? I mean, the algebra of this set can be backtraced to this set of algebra. That is, so you can create all the full A double prime from this A. But that is not true in the algebraic level, but it is for von Neumann algebra, it is true. Okay, let me. So one important point is that this is an important consequence, that even if A is not a von Neumann algebra, but A complement is always a von Neumann algebra. So this proof is very easy, that so we actually need to show that is A prime is actually closed under weak limit. So let's assume that A1 prime, A2 prime.
Suchetan, you are using prime for complement or commutant?
Prime.
Yeah.
No, here commutant. I mean.
So in this
A1 prime.
No, A prime, is it A?
Oh, this means commutant, not
complement, right?
Or something. This commutant. Commutant means the maximum set of.
No, I thought you said complement, but.
No, sorry.
Okay.
A prime is a commutant algebra. This is commutant. This is not. So suppose we have a sequence of operator which belongs to a prime, I mean the commutant, and then it has a weak limit which is a prime. Okay, so we have to see that this a prime can be included in A. We have to prove that. Okay.
Why?
So it is very easy that suppose take any two psi and chi. So let's consider this object.
So what are you trying to do here? You're saying that if A is a von Neumann algebra, then A double prime is also
A prime, just A prime, not
A
sorry, not
prime.
double prime.
Okay.
A prime.
Okay. So
A prime, even if A is not a von Neumann algebra, A prime always von Neumann algebra.
But what is A? I mean, what is the constraint on it? Like,
A.
yeah.
A can
A
be
is any
such-
algebra, any star algebra, sub-star algebra, but it is not closed under weak limits. Suppose A is not closed under weak limits, but A prime is always closed under weak limits. That is the point.
But then why are you saying A prime should be in A and not small A prime? Why are you saying it should be in the
Small A prime. Huh?
Ah.
No, I have
It
to see
should
that
be in-
it also belongs to A.
Why A? Why should it should be in A prime, right? You're saying A prime is the von Neumann
Sorry,
algebra.
sorry, A prime. Sorry. Thanks. Yeah. So let's consider this object. Okay. So now it can be written as like since I use just the weak limit A, this is the A prime, right? Weak limit is A prime. Now by definition this A sorry. So by definition this A and A n prime is commute, right? Because A belongs to here A belongs to A. And A n prime belongs to A prime. So it is 0. That means if it is 0, then it means and it is true for any psi and chi. That means A prime is 0. So that means A prime belongs to. So it's easy proof.
So you still need time to finish? Sorry, just because the tea
Yeah,
is
yeah.
ready and it's getting cold. That's why this.
Oh, let me finish now that. But I.
No, if
I don't
there's
think I have
something.
some, but Debangshu can carry out. I mean, from the next time, right? From there. Yeah. There's nothing. Just some half duality and something else. You can. Okay. Let me stop here. I mean, this.
Okay.
So okay. So that is the point that I'm just saying that we have defined the von Neumann algebra, and we defined that if A is a von Neumann algebra, then if A is any algebra in Star algebra, then A prime is always be von Neumann algebra. And I just stop here that for von Neumann algebra, which I am just saying that A equal to von Neumann algebra. Okay. And this.
So I just got a bit confused with the proof. So if A prime exists, it belongs in. I mean, if small A prime exists, it belongs in A prime. That is true.
Yes.
But how are you certain that the A prime exists to begin with?
No, we just I assume that if A exists, there is an exist of weak limit, then it must be in A prime.
I see.
That I proved that. But I mean, it is not. I mean, that language of mathematics. I mean,
Okay.
that, yeah. If that exists, it is not an if and only if statement, of course.
Okay.
It is if it exists.
If
then
it exists.
So I just mentioned one thing that for von Neumann algebra, A is always A double prime, and since A prime is always in von Neumann algebra, then A double prime, A prime is A triple prime. This. These are two properties. Actually, later you will see that even the any open set in the Minkowski spacetime, it also follows this two property that, and if you have any open set U, then U and U prime is a causal complement of the U, then actually U equal to U double prime, and U prime equal to U triple prime. You can actually see this. So there is an one-to-one analog between open set in a region to the von Neumann algebra. I mean, one-to-one correspondence. So and from this we can see that I mean, von Neumann algebra of any region A is basically the algebra of operators in the causal domain of different. So when we call something von Neumann algebra of A, it is always defined as the von Neumann algebra or the algebra observable or full causal development. Okay. Well, it can be followed from, I mean, some duality called Hug duality, which will, I mean, Debangshu will be told next lesson. You can continue from this. Okay.